Section 10.2 is going to continue talking about with circles. That's the whole trend, common trend. But we're going to actually hit on some ideas we discussed already in Chapter 11. So one thing that we did to kind of help this speed up the process is you'll notice if you have the note-taking guide, we have these vocab and things already typed up for you. We're also going to speed through this kind of quickly. So if you don't have a note-taking guide, just keep in mind that we've already defined these. So if you want to kind of summarize it or look back in one of the sections from Chapter 11, I can't remember which section. It might have been Section 4. I think that's what it was. We've already defined these. We're just going to do a quick recap, essentially. All right. So first of all, we need to remind ourselves what a central angle is, because that's going to be involved a lot in these upcoming sections, okay? So a central angle is an angle whose vertex is the center of the circle. All right, so in this picture, if I told you this was circle A, what would be the central angle?
Angle BAC.
So angle BAC would be the central angle because of the fact that its vertex is at the center, right? Now, the measure of a central angle is the measure of its intercepted arc. Now, what is the intercepted arc we're talking about?
Arc BC.
So we're saying that is equal to the measure of arc BC. Remember how we talked about that?
Yeah.
Now,
the measure.
Measure, sorry. Yeah. Measure of the angle. Sorry. I wrote angle BAC, was not talking about measure at that time. Yes. Now, notice how I wrote the arc. And the other thing to keep in mind, this is talking the measure. The measure of an arc is the degrees, okay? Right. And that's because we're talking about angles being, that angle being the same. All right?
Okay. Next, we've talked about minor arcs, major arcs, and semicircles. And like I said, we've already said this before, so this is just a refresher. A minor arc is going to measure less than 180. They're named just by their endpoints, just like we had on that last one. We said arc BC, so only named by their endpoints. And the measure is the same as its measure of its central angle. Major arcs are going to be a part of the circle that is between 180 and 360. So larger than a straight line, but not quite the entire circle. Okay. They're named by their endpoints and by a point on the arc. So it's got endpoints and a point on the arc. We didn't use these too much in Chapter 11, but like if I had said this is point D, what's the major arc that I see
here? We could say arc BDC.
So going from point B all the way through D to point C.
Okay.
So I'm going to go ahead and say arc BDC would be the name of that. You're going to know it's a major arc because it's got 3 letters.
Okay.
Okay. To find its measure, keep in mind that it's got an associated minor arc with it. So this major arc and this minor arc together
make up 360.
So if I know the measure of this arc BC, I could take 360 minus the BC, and that would leave us with what's left.
Okay.
Okay. The semicircle, hopefully we know what a semicircle is. It's when it's measuring exactly 180 degrees. Named similar to a major arc, though.
Yeah.
So it's going to have their endpoints and a point on the arc, so we know which way we're going to be talking about for that specific semicircle.
Okay. So what we have is a circle, of course, with, notice that I have some radii drawn in, and that's essentially central angles are formed by some radii. Okay, just a reminder of that too. So what we're going to do is we're not going to name every central angle or name every minor arc in this picture. Just name a couple just to make sure we're good. Okay.
All right.
Now, starting with some central angles.
So
now,
like SPT would be a central angle.
So angle SPT. And notice I'm not naming it just angle P because there's several angles with that same vertex.
Right.
So this would be a central angle. Right?
Okay.
Can you name me another one?
What about QPT?
Yeah.
Just to make it look a little different.
That would work. That is a central angle. All right. Okay. Let's move to some minor arcs. Now, minor arcs, remember, I'm going to make a note, they measure less than 180 degrees.
Okay.
So keep that in mind. So let's name some minor arcs.
Okay. Well, I'm looking at the 62 degrees. That's definitely less than 180. So arc ST is a minor arc.
And I like that she was kind of looking at the central angle because remember, the central angle is the same as its intercepted arc. So this would also be 62 degrees.
And I also know, like, for example, the 35, each of those smaller ones seem to be, but what if I put those two together? The 35 and the 118, that still is less than 180.
Now, how would you name this arc that you're talking about right here? It's a minor arc.
It's a minor arc, so it's just going to be arc QT.
Now, this brings up a good point, because how do you know which arc you're talking about? How do we know if we're talking about this other arc right here?
Well, because that is a major arc. That is larger than 180 degrees.
So I love that. So again, when you're naming minor arcs, you just need 2 letters every single time. So thinking of major arcs, all right? So going with what we just talked about, so we know that this is the minor arc. The major arc associated with that would be arc
QST.
Now you could put that in different order, just like these. You could do TQ, you could do arc TSQ. Now, could I name this arc QTS?
No, because we have to have the point that's on the arc in the middle.
Okay.
And the end points of the arc are the 2 ends.
And if I named arc QTS, that would be this arc right here.
Now, that's another major arc.
So let's just do that. QTS. So as long as they're more than 180 but less than 360. All right. Semicircles. Now, what do we know about semicircles?
That they measure exactly 180 degrees.
Okay.
And I do notice that if I add together the 62 and the 118, those do measure 180 degrees together.
All right. So how would we name a semicircle?
By, again, 3 letters, so just like a major arc. So I'm going to call it STW.
Now, do you see another semicircle?
Well, if that side's 180, the other side has to be 182. So arc SQW is another semicircle.
And this is why you have to name it with 3 letters, because which semicircle are you talking about? That middle letter, middle point, is going to tell you which one.
Yeah. All right. Congruent arcs. 2 arcs of either the same circle or of congruent circles are going to be congruent if they have the same measure.
So this is actually a new term.
It's a new term. When we're talking about congruent arcs, now it makes sense if they're in the same circle, that if they have the same measure, then those arcs should be the same length also. Okay. Because they're the same degrees, same portion of that same circle. All right. It gets weirder when we start thinking about congruent circles.
Or if they're in different circles, if they're not congruent, then they're not going to necessarily have the same measure. They have to be in congruent circles if you're talking about.
So, first of all, can we say that arc AB and arc CD in this picture are congruent?
I would say yes on this.
Okay.
And my reason for that would be because they're in the same circle and they have the same measure. And I know it doesn't say explain, but we're pretty good about asking that. So,
all right. Now, this one. Take a look at these 2 circles. What do you notice about these 2 circles?
Well, if you ever are talking about congruent arcs and they're in different circles, the circles have to be congruent. And I notice that in both of the circles, they have congruent radii, so the circles are congruent.
Okay, that's important. You have to know that.
So if that wasn't even the case, then we probably wouldn't
go any further.
Okay.
Okay. Now, both of the central angles measure 135 degrees. So are their arcs going to be congruent?
Yes, because they're in congruent circles and they have the same measure.
Love it. Now, take a look at this next one. We know that arc AB is based off of this central angle.
Now, arc AB is a minor arc, right?
Actually, that's kind of a major arc.
But if we're naming them, we're talking
another point on
we're talking about the other one though.
Okay, so we want to know what this would be
150. So the reason why I bring that up, that's something to keep in mind, because when you name an arc, the name does tell you which arc you're talking about. We're not actually talking about the other one, even though that 210 kind of looks like we're talking about it. We're actually talking about the minor arc, which is the 150 that goes along with it.
Right. So if this central angle is 150, the question is, does that mean that this arc is going to be the same measure as this arc?
Or congruent? Well,
congruent, sorry.
They do have the same measure.
Same degree measure.
They're both 150 degrees.
Do they have the same length?
Well, they're not going to be because they're not in congruent circles.
Right.
One circle is obviously not. So because they're not congruent circles, which then who cares about the measure because they're not going to have the same length.
Right.
And guys, you also think realistically here. If you like cut along that A and B and the C and D and straighten it out, their lengths are not going to be the same.
Obviously, that AB is going to be shorter.
All right. Now to some postulates, and then we have some theorems as well. Now, postulates usually are those kind of no-brainers, all right? And this is something that you guys have done before. It's not that tricky.
Right.
It says arc addition postulate. Now, we've had angle addition postulates. We've had segment addition postulates.
And they all basically just said,
now,
add them together and you can get a larger piece.
So we're going to be adding arc measures together, okay? So it says the measure of an arc formed by two adjacent arcs is the sum of the measures of two arcs. So if you want one big arc measure and it's formed by two adjacent arcs, now keeping that in mind.
So next to each other.
Then the sum of those measures of the two arcs will equal that, okay? So in this case, let's say I have arc AB, which is right next to arc AC. If I add the measure of arc AB to the measure of arc AC, that's going to give you the measure of arc
BAC. And now I'm just looking at the picture that appears to be more than, it appears to be BAC.
Or major.
I don't know that for sure.
Yeah.
It could still be a minor arc to where I would just call it arc BC. So just something to be careful with. We'll know more specifically.
And usually, guys, you'll know with the degrees. But the whole idea is this arc plus this arc will get you this whole entire degree measure. Again, kind of common sense.
Right. All right. Theorem. Here we go. I've got a few of these things today. So this theorem says, in the same circle or in congruent circles. You're going to notice that's going to be a common trend too. Because a lot of things, we can't do things with them or have any special relationships if there's no special relationships with
the two
circles. So either in the same circle or in congruent circles. Two minor arcs are congruent if and only if.
Biconditional.
Means it's going to work both ways, right? Their corresponding chords are congruent. We haven't talked about chords yet today. So let's refresh our memory on that vocab term. What is a chord?
A chord was just a segment with endpoints on the circle. So like in that picture on the left, segment AB and segment EC are both chords.
Exactly. So this theorem, and again, it works both ways, says that if the chords are
the minor arcs,
if the arcs are congruent, then the chords will be congruent. So if the arcs have the same lengths, the chords will have the same lengths, and it works both ways. So if the chords are congruent, then the arcs will be congruent.
Okay, that kind of makes sense.
Now, this one, notice that I'm showing what's special about these two circles.
They have congruent radii, which means the circles are congruent.
Right. So now, the same thing is true. If within two congruent circles, if you have arcs that are congruent, so if the circles are congruent, which I know, and I know that arc JK is congruent to arc PL, then what do I know?
Put an arc.
Oh, yeah. Thanks.
Then segment JK is going to be congruent to segment PL.
Right.
And or vice versa.
Or vice versa.
Kind of flip-flop. So
That's
really,
true.
if and only if.
Yeah, I don't even need an if and then. I'll just say if and only if.
Yeah.
Same thing over here. So I could write that a arc AB is congruent to
arc CE if and only if segment AB is congruent to segment CE.
Oh, CE.
Now, while she's writing that, I want you to also keep in mind, I know the theorem says the minor arcs, but I want you to think about, like in the picture on the left, if you know the measure of arc AB, would you know its major arc that it's associated with? So like the arc A, maybe C, B, however you want to name that. Okay, so you would know that measure. And then the other one, the arc EBC, wouldn't those be congruent as well?
They would.
So even though it says 2 minor arcs, you can even talk about the major arcs as well. So you might make a little side note, maybe up there, just say also works for the major arcs. And that goes true in that one picture on the right. So that major arc that it's associated with, this will be congruent to that one as well.
Awesome. Love it. Okay.
All right, this next theorem, notice it's not a biconditional. It starts within just an if, so this is strictly a conditional statement, and so it only works one way. So you have to, it says if a diameter of a circle is perpendicular to a chord, okay? So if you know a diameter, all right, so how do we know when something's a diameter?
Because it goes through, it's a chord that goes through the center of the circle.
Okay, so in this picture, what do you think would be the diameter?
EG.
And that's because notice the center is point I. Now, this is also a chord, but it's not going to consider the diameter because it doesn't go through the center. Okay, so in this case, the diameter we're talking about is segment EG. I'm going to make a little note. Of a circle is perpendicular to the chord, to a chord. So in this picture, it would be
DF.
DF, all right? So if I gave you this was happening, they're saying then the diameter will bisect the chord and its arc. This is kind of the key here. All right, so if I know, it's really sticking here. If segment EG, again, this is the diameter, okay, is perpendicular to DF, segment DF, which is a chord. Now, could it be perpendicular to another diameter? Yeah, because the diameter is a chord, okay? So just make sure that you're knowing which one for sure is the diameter. So keep that in mind. Then the diameter is bisecting the chord in its arc. So let's think about what that essentially means. So this is going to bisect the chord. So what is that going to mean?
It's that segment EG is cutting segment DF into 2 congruent pieces.
So what pieces are going to be congruent?
DH and HF.
So we can say then DH, segment DH is congruent to segment EF. Now it says it's also bisecting its arc. Now what arc are we talking about?
The arc has to be the one that's associated with that part. So like, well, really it's going to bisect a couple different, but like if I'm looking at arc DF,
that's the arc it bisects.
The arc that it's bisecting.
So arc DG and arc GF are going to be congruent.
Right.
Now you said something, and I like that you said that because you kind of paused. We often think that here. This arc is one thing it's bisecting, but it's also bisecting what arc?
Arc DEF.
This arc right here, because it's also associated with that. So that means we could also say
and we could also say that arc DE is congruent to arc EF.
So several different things are going to be congruent, which is kind of cool. Something to also notice is that this diameter ends up being a perpendicular bisector of this chord. So something also to notice there.
In fact, there's so many relationships in here.
Oh my gosh.
It's amazing, and it will really take us back to chapter 4 again when we start looking at some of the relationships. All right. Next one. This picture looks a lot like the last picture, okay? Now, this one says that if one chord is a perpendicular bisector of another chord, okay? So, let's talk about that for a minute. So let's talk for a second. What does that mean? Okay, so, well, we would have to be shown that. So let's say the JK is, because you're going to have to be told this. You're not going to be guessing. Let's say segment JK is perpendicular of the perpendicular bisector of segment ML. And again, guys, this is not something you're just going to make up. This is something you'll give it. You will have
so
to
that basically means that they're perpendicular and it's bisecting ML, so that means MN and NL are congruent.
Okay. So if that happens, then the first chord is a diameter.
So the chord that is not being bisected, the thing that's doing
the bisecting, yes.
So that means that segment JK is the diameter. which kind of in a sense is somewhat the converse of it, but notice this one has nothing to do with arcs.
Right.
But if you know now that's the diameter and it's perpendicular to chord, then we know arc MK is going to be congruent to arc LK and all that other stuff. So there's a lot of things that you'll be able to tell.
Lots of relationships.
Which then you also know, like, if you know it's a diameter, you know what the radius is, and all these different things.
Awesome.
All right, last theorem, and then we'll do a few examples. Not a ton of examples, just a lot of information.
A lot of information.
It says, in the same circle or in congruent circles, this is kind of like a couple theorems ago. Two chords are congruent if and only if they are equidistant from the center. So here's one thing that I'm noticing.
It's biconditional.
It's biconditional, so kind of going forwards and backwards. All right, so this is one where you're talking about in one circle, and then why are these circles congruent?
Because they have the same radius.
Okay. So this will work in either scenario. Notice the last two theorems only worked in one circle. So one thing to keep in mind. So it says two chords are congruent if and only if they're equidistant from the center. So two chords are congruent. So in this picture, what do you think the two chords are talking about?
Arc CD and arc AB.
No, we're talking about chords.
Oh, sorry. The chords are good. Segment CD and segment AB.
Now, if you knew these chords are congruent,
the arcs are going to be
then
congruent
the arcs
too.
are congruent.
I'm putting them all together.
Yes. So again, notice the connections between them all. She was just kind of thinking ahead.
I am, because I know there's an example.
Yes. So if the chords are congruent in one circle, then their arcs are congruent as well. Okay. Yes. Now, if and only if I can write here, then if and only if they're saying. Now what are they saying they?
The segments, those chords,
are equidistant from the center. Now, this is where you got to think back really to chapter 5. This is when we start talking about distance from, it says from a segment to a point. So you're talking about from here to here.
That perpendicular distance.
This has to be perpendicular. So when you're talking about the distance from a segment, line, ray, whatever, something linear to a point, it has to be perpendicular distance. So I want you to write that as a reminder. So if I did not give you this perpendicular, you wouldn't be able to say those are the distances.
Right.
So if I gave you these are the perpendicular distance, then you will be able to say that these would be congruent as well.
Right.
Okay, so if and only if, basically in this case,
that segment EG is congruent to segment EF.
And again, that's only because these are perpendicular distances. All right, I want to just, again, remind you of that. Right now, and over here, kind of similar idea, congruent circles. We have two chords, so it would be segment AB is congruent to, say, segment RS. That's what either you're given or you're trying to decide.
If and only
if. If and only if.
And now here, they don't really label a specific point that's on there.
So let's draw that in.
Let's do.
So if I'm going from the center to the chord here, if I'm talking about the distance, I want the shortest distance. So I want
the perpendicular distance.
So I'm just going to call this E.
Okay.
And then from here to here, we'll call this F. So then we can say if and only if
CE, segment CE, was congruent to segment TF.
Now again, going back what Ms. Hogarby said, just like the first theorem we learned, if these chords are congruent, then their arcs are going to be congruent. So there's lots of different things that are happening. Now, another thing to kind of keep in mind, and I'm just going to stress this here, is that this perpendicular distance, notice it goes from the center. If I extend this out, it actually is part of what segment?
Oh, it's part of that diameter.
Okay, so just kind of keep that in the back of your mind, okay? So when you draw the distance from the center perpendicular to another chord, that's actually part of a diameter, something that
goes along with another theorem. Okay. So some examples. First of all, just find the measure of each arc, because I want to make sure that we're comfortable with, first of all, is it the major, the minor, and which way we're going to go. So if I ask you to find the measure of arc MR, I know that, is that going to be a major arc or minor arc?
That's a minor because it has two letters, so it has to be less than 180.
Right. And if I add these two arcs together using that arc addition postulate,
so
is that less than 180?
Let me double check. Yes, it's 165.
And you got that by just taking
98 plus 67.
Love it. If that hadn't been, then I know I'd have to be talking about the other side.
Yeah, sometimes our pictures aren't drawn to scale.
All right. Now we're going to find the measure of arc VMR. So starting from V, going through M, and all the way to R, which the nice thing is they give us all those measures. So I'm just going to be adding an 85 to a 98 to a 67.
Or you could take 165 and add 85 to that.
Because
since we
know
just
this
did that. And I already have it in my calculator from before, so it's 250. Now, notice because there's 3 letters, I knew it was going to be either 180 degrees or more because it's either a semicircle or a major, and it ends up being a major arc.
All right, what about the measure of angle VSR? So now when we say VSR, we're talking about this measure right here.
Okay. So I know that all those other angles added up to 250, and I know that all of them together add up to 360. So if I can just take 360 minus 250 and get 110.
Love it. And that measure of the angle is the same as the measure of its intercepted arc. Next one says find the measure of arc MVR. So M through V all the way to R. So what is that including?
That's including arc MV, so that's the 85, and the angle VSR, which is what we just found, 110. So I'm just going to do 110 plus 85.
Yep.
And that's going to get you 195.
Awesome. Basic example.
Yes.
Let's move on to more fun.
Okay, so this next one here, it says find the measure of arc DC. Okay, so if we were going to find the measure of arc DC, right, let's think about what we do have in the picture.
All right, well, I see 2 chords that are marked as congruent.
Okay, and that probably has something to do with this.
Uh-huh.
So the fact that they have things labeled, these are actually associated, is it with the chord?
Or no, those are with the arcs.
Okay, notice again, arcs are measured in degrees. Segments obviously are not.
Right.
Right. So what does these chords have to do with those arcs that are labeled?
Well, we learned a theorem that says that if the chord or if the chords are congruent, then the arcs are congruent.
So that means this arc DB, so I'm going to make a little note, arc DB is congruent to arc BC. Now, the reason why I point that out is because that's the given information. But notice what we're trying to find.
Is another arc.
This arc right here. But if I know the measure of these arcs, that will help you find arc DC. So
Definitely.
just kind of keep that in mind. In the end, the measure of arc DC is what we're trying to find.
Okay.
Okay? Now, since these are congruent, we can just set them equal.
Sounds great.
So just an equation, and this is a pretty basic one. So I'm going to get x equals
37.
37.
Yep.
All right. Now that's just the x.
Right.
So what do you think we're going to go next?
So I need to actually know the measures of those 2 arcs to be able to find any unknown measure of an arc that's left.
Okay. So what am I going to do with
So
that?
I'm going to take like 3 times 37 plus
Okay.
11.
And that gets you
122.
Now that's arc BD. We wanted DC. Now that
Okay.
should also be.
It should be the same thing as arc BC, 122 there.
And if you wanted to double check, just type in 2 times 37 plus 48 and see if you get 122.
And you do?
And you do. Now, where am I going to go now?
Okay, all 3 of those arcs together, the DB, the BC, and then the DC, which we're trying to find, all make up a whole circle.
Okay.
So they're all 360. So if I take 360 and I subtract the 122 and another 122,
So 2 of those.
2 of those, we'll end up with 116 degrees.
So basically you're subtracting 244.
244.
116. So that's the measure of arc DC.
All right. Now, looking at this next one, we have lots of different segments drawn in this circle. And they just say find CG. So CG is just this little segment right here. I'm going to highlight it just so we see it. Okay. Now, they give us all kinds of information. They tell us that AB, which is a chord, is 12. They tell us that DE, which is another chord, is also 12. What do you notice about those two chords?
They're congruent.
When the chords are congruent, that also means that the
arcs are congruent.
Arcs are congruent. We know those things. They also tell me that CE is 7.
Okay.
Now, let's take a look at just some of the information that we've got, and let's talk about it in terms of some of the theorems that we know, because there's some things here that there's a lot of really cool relationships.
Okay. Well, what I'm noticing, first of all, and like I did mention that the fact that the arcs are congruent, but I'm noticing this problem doesn't say anything about finding the measure of the arcs, so probably not going to be helpful.
Probably not.
Okay, but what I am thinking that, I'm noticing some perpendicular distances, and I'm thinking to one of the last theorems we learned. Can you go back to that slide real quick?
Sure. Let's see if I can find it.
The next one.
Yep.
Okay, so if you have in the same circle, which we do have, if two chords are congruent, then they're equidistant from the center. So the two chords that we talked about that are 12 are congruent. So they're equidistant to the center. So I'm going to have you go back.
So like these two measures are congruent.
Go back to that. So that means since AB and DE are congruent, that means segment GC and segment CF are congruent. Now, the reason why I point that out is because if we can find CF, I can find CG. And the reason why I'm leaning towards that is because they give you something about CE that kind of is related to that CF.
Right.
It forms a right triangle there. Okay?
Right.
Now, the other thing I'm noticing, and this is going back to something I mentioned earlier, was that segment that goes from the center and perpendicular to that chord, if I extend that out, like I was talking about on that slide, that is a diameter as well. So...
And we learned the diameter, when it's perpendicular
to a chord, it bisects it. So that means segment DF is congruent to segment FE. So that means segment FE is 6, and that's the reason why I'm focusing on that one, because I see a right triangle.
I'm going to draw that little right triangle.
And in a right triangle, okay, the right triangle, I can use Pythagorean theorem to find that missing piece.
Love it.
All right, so let's set that up. So it would be 7 squared equals... Is that CF? Yes, CF squared plus 6 squared. So you're going to get 49 and then 36. When I subtract that, I get CF squared equals 13. So CF is the square root of 13. Now
that's as exact as we can get.
That's just CF. It asks for...
They ask for CG.
But we already said CG and CF are the same. So CG is also the square root of 13.
And notice that they don't have units on anything here. So we can leave it as that exact form of just radical 13. I love it. Look at all of those relationships that we've learned today within one circle. Kind of amazing.